Hello everyone. In this talk, I'm very happy to discuss my recent work about formulations and constructions of remote state preparation with verifiability with applications. I'm Jiayu Zhang. So this talk is about quantum cryptography primitive, remote state preparation with verifiability, or RSPV. We will first discuss the backgrounds and discuss our contributions on framework, constructions, and applications. Let's first go to the backgrounds. Recently, there is an emergence of quantum cryptography. Quantum computations is cryptography to ensure its security. And on the other hand, quantum information technologies also make cryptography better. For examples, there are a lot of works on quantum key distributions. And we could study verification of quantum computations. And there are a lot of primitives with quantum outputs, which is also a very popular topic. And there are also many other problems and topics in this field. In this talk, we focus on a basic primitive quantum cryptography, which is RSPV. So what is RSPV? Consider the following setting. There are a client and a quantum server. The client would like to prepare a state and send a state to the server. And here the states denoted by psi is randomly sampled from the state family. For example, a plus theta states, or BB84 states, or some other states. The client would like to prepare a state random sample from these state families and send the state to the server. The clever solution is to use a quantum channel. To prepare the states and send it by a quantum channel to the server. And in the end, the client knows the description of the states because it prepared it by itself, and the server simply holds the states. And we note that in the quantum world, holding description is much more powerful than holding the states. For example, by holding the description, you could clone the states, but if you simply hold the states without knowing its description, you could not clone it in general by the no-cloning theorem. So this is the trivial solution. And consider the following setting. What if the client is completely classical? So it wants to use classical computation and communication to achieve similar things. And the states need to be locally prepared by the quantum server. So we want to design a protocol using only classical communication so that in the end, the client still holds the decryption of psi and the server holds the state psi. What's more, we want the protocol to have some kind of security, which roughly means even if the server cheats by doing some malicious behaviors that might be different from the honest behavior, there should still be some kind of security, which in more detail means the joint behavior of the client and server should be simulated by the honest behavior, which is roughly what is shown in this diagram, where the client holds the decryption and the server holds the state. So this is the RSPV primitive. And this primitive is very important in quantum cryptography. That's because this primitive could serve as a protocol compiler. When we design protocols, we could first design a protocol where the client prepares sends some quantum state to the server. And we could use RSPV to compare this protocol to another protocol with only classical communication. And this is an important tool for studying other problems, like classical verification quantum computations. There are a lot of works on this problem and related problems. And in these works, people design RSPB protocols with different properties and use it to compare. For example, verification quantum computation protocols to a classical verification quantum computation protocols. So, how about the detency of RSPB? Currently, we know that RSPB exists for some state families. For example, plus theta states. Plus theta states is an important state family in quantum cryptography because it's sufficient for important problems like verification quantum computations. And in paper GB19, CQW19, we have achieved an RSPB protocols for plus theta states, which implies the existence of classical verification quantum computation protocols in this RSPB approach. And the constructions need to rely on cryptographic assumptions, which is the LW assumption. And in later work, people improved the existing results in different ways and study and achieve RSPB for tensor products of plus theta states. So there are a lot of existing works on RSPB, and existing works also have limitations. For example, there are many various definitions about RSPB in the literature, and these definitions are not always sufficiently well behaved. Well, if we want to build more complicated protocols from simpler protocols, some definitions are relatively more well behaved, and some are relatively less well behaved. And there are a lot of subtleties in this part. And there are big open problems with existence of RSPB. Existing RSPB focus on very simple state families, like plus theta states or their tensor products. But we don't have a general solution for RSPB for general state families. And we would also like to see more application of RSPB. In summary, we want to study its formulations, constructions, and applications. So let's go to our contributions. We will first give a new framework for RSPB problems. So the motivation is, we would like to construct more advanced RSPB from smaller pieces that are relatively easier to construct. In more detail, we first choose more well-behaved variants of notions among all the possible variants in the literature. And then, using these notions, we study and prove its basic abstract properties, which is, in more detail, we study its critical composition and soundness application. Later, we will use this framework to construct concrete protocols. So in more detail, what is critical composition? Critical composition means given RSPB for state family F1, F2, F1 and F2 are two different state families. And by sequential composition, we could construct a new RSPB for state family F1 tensor product F2. So if the target state family could be written as a tensor product of two simpler state families, we could first build RSPB for these two simpler state families and do sequential composition to get a more advanced RSPB. It also implies that if we have an RSPB for state family F, we could do an n-fold sequential composition to get an RSPV for state family F tensor N. The n-fold tensor product of state family F. And then we have solid amplification. We define a variance of RSPV called pre-RSPV. In this variant, we relax the soundness requirement. And this notion is easier to construct and could be amplified to RSPV. And in our framework, we have also introduced a new primitive called RAV, or remote operator application with verifiability, as the operator analog of RSPV. On the one hand, we consider it as a cryptographic analog self-testing, which is studied in a lot of previous papers. And on the other hand, it is an operation analog of RSPV. So in RSPV, it is certified that the server gets the states. And in RAV, it is certified that the server applies the operation. We note that the concrete constructions for this primitive is still an open problem. So this is our framework. And then we construct different RSPV protocols for some new state families. And we consider the following two results particularly interesting. We construct our RSPV for state family 0x0 plus 1x1, where x0 and x1 are both long strings sampled from 0, 1 to the n. This is a new state family. We know that previously there are a lot of works about creating this type of states with some other type of security. But its RSPV construction is not known previously. When we have also constructed a new RSPV protocol for plus theta states. This is achieved previously, but we recover the result in a more modular way. Overall speaking, we construct sequence reductions between different RSPV primitives. We start from RSPV for BIP84 states, 0, 1 plus minus, which exists by a previous paper. Then we construct new RSPV protocols step by step, starting from these states. So we don't need additional cryptographic assumptions in the middle. The cryptographic assumptions is only used when we try to construct RSPV for BIP84 states. What's more, each step is either a direct application of our framework or something with a simpler intuition, or we only need to analyze the information theoretic core. And since the analysis is purely information theoretic, it is easier to handle compared to cryptographic problems. And this is our reduction sequence. We know that in the middle, there seem to be some states whose representation is low. But we note that these steps could be classified into the two classes that we mentioned previously. In the blue step, we simply use our construction framework or something simple. And in the red step, we analyze the information theoretic core and use our framework to achieve this step. So we could see, after some intermediate step, we could achieve RSPV for, we could transform RSPV for BIP84 states to RSPV for states 0, 0 plus 1x1. And then using RSP for these states, we can try RSP with plus theta. Let's focus on the first step as an example. How could we go from RSPV for BB84 to RSPV for this state? So what does this state mean? It means that in this state family, x0 and x1 differ in only one bit, and x0 has total parity 0, and x1 has total parity 1. And x0 and x1 are all n-bit strings. So these type of states could be equivalently written as the tensor products of lotto 0, 1, and 1 plus state. And there's no minus states. So what we need to do is to simply repeat the RSP for B84 states by many rounds. And pick the states, and the client could simply tell the server which states it wants to pick and keep. And the server could simply pick the states needed and discuss the other states. And these other steps also works like this. We either use our framework or simply use some simple transformations that has an easier intuition, or we analyze the information theoretic core and compare the information theoretic core to a formal protocol with our framework. So let's go to the applications. We could apply our result to the classical verification quantification problem and achieve this primitive for weaker alternative assumptions. So what is CVQC? The setting is similar. There is a classical client and a quantum server. The classical client would like to verify a quantum computation. For example, if we want to verify that the output of evaluating a quantum circuit C is indeed 0, or is indeed 1, as claimed by the server. And the server might cheat. And if the server cheats, the client would like to catch its cheating behavior. So there are many works on these problems. And the most famous one is possibly Mahadev's 2018 construction. And there are also many other improvements on this construction. But roughly speaking, existing CVQC all rely on the limit 0 assumptions, which is cryptographic assumption. But if LW is broken, then this existing CVQC, roughly speaking, become very hard to instantiate. But with our work and existing works, we have different construction. First, we know that by these existing works, we could have an RSPV for BIP84 states from alternative assumptions, which is about cryptographic group actions. Then combine these results with our results. We get RSPV for plus theta states from the same assumption. For the reduction sequence, we could go from RSPV for states to RSPV for plus theta states. So we could achieve RSPV for plus theta states from the same assumption, cryptographic group actions. Then we could use this RSPV to compare our existing verification quantification protocol, FKD18, to get a CVQC from the same assumption. In summary, we achieve CVQC even if LWA is broken. Thank you very much.